Thanks a lot. I wanted to first acknowledge that my were probably volunteered for this particular talk, so don't blame them if they bothers you. I want to talk a bit about the rocks distribution on the moon. Work at NASA Marshall, one of the things I used to tell the engineers is the moon is much less scary than Mars. So sometimes they had this vision of Mars Viking landing site when they were worried about trying to put a lander down on the moon. And it's just not that rocky a body, okay? That's a very fundamental fact about the moon that you need to understand. And so Diviner showed this beautifully in Josh Banfield's work that has been followed up by Tyler Powell that shows that the typical rock abundances are, of the order of 0.3%. That's kind of the median. There is a long tail of rock abundance that goes out to 20% or more at the 200 meter per pixel resolution of Diviner, but that's not. It's a very small fraction of the surface, a millionth of the surface or something that has that many rocks. Most of the surface is rock poor. And the reason for that is because the moon is undergoing a slow motion demolition job. Okay, it's like a construction site. They put out TNT every now and then and blow the place up. A calculation I did using the Gerhard-Neukomm's production function is that even if you just look at the 10 to 500 meter crater forming bin, you've put down per square kilometer not that different an amount of ordnance as you would have used in all of World War II, summed up, including the atomic bombs. And that's per square kilometer per billion years. And so, really, it's blowing up a lot. Okay, so if you're a rock on the surface of the moon, you're likely to blow up. Another way to look at this is every point on the surface has been hit by the equivalent of 2 impacts that'll form a 10-meter crater in the last billion years. So the 10-meter craters turn over really, really fast, and so this is why rocks don't survive. This has been looked at by other people. Sasha Basilevsky has done a really beautiful work on this, showing the half-life of rocks is of the order of 100 million years or less. There's also recent work by Roosh et al. That I'll point to. There's been about 5 or 6 papers by Roosh, Wohler, Bickel, etc. in the last 5 years. They're all amazing. They're all really cool papers. Go read them. But the moral of the story is that rocks get blown up. This demolition job is a real thing, right? They don't have a long lifetime. So this raises the question that's the point of this talk. It's where are the rocks if they mostly are blowing up? Well, they're around landforms that are fresh, the youngest landforms on the moon. So these are the places where this list is the places where I would expect rocks. Fresh impact craters are canonically great examples. I don't know how well this shows up on the screen, but you can see all these little dots in the LROC, beautiful LROC image. These are each individual class of material that's been excavated from underneath the surface regolith. And certainly the proximal ejecta of craters, I think, is my mental picture of the moon is that's where most of the rocks are. The second place that rocks are areas of high curvature or high topographic slope. And these are interesting because high curvature areas on the moon can persist for billions of years. So if you look around the Imbrium Basin, its mountains still have these very high topographic slopes and curvatures. And that's why when Jack Schmidt gave his talk yesterday, we saw those rocks on the surface coming off the walls still. It's because the high curvature can persist for billions of years. And at those high curvature locations, rocks can be excavated by the removal of objecta down the steep slope and basically the exhumation of rocks from beneath the surface. And this can last many billions of years. So high curvature areas, those make sense. The next one is a little bit more enigmatic to me. These are tectonic landforms, scarps and wrinkle ridges. It turns out that many of the wrinkle ridges on the moon are just associated with just incredible dense concentrations of boulders. And under the Dell command update there, Valentinus and Schultz wrote this really interesting paper a few years ago showing how clustered some of these rocks are on the surface of these tectonic landforms. And they had a particular model for how they might get rocks there. I'm not totally sure how this works, right? Like maybe it's they're being pulled up with the throw of the fault, and the faults are active still today. I think there's good evidence of that. Maybe the motion of the faults removes material from the slopes around preferentially and triggers little landslides that expose material by exhumation. That's something that Nick Schmurr talked about on Monday in a meeting I was in. And I think it's a very clever idea. I think that's possible. But I don't totally get why there's a lot of rocks around these landforms. They're also probably young, right? So it's probably young exposures in the last 100 million years or less, maybe even millions of years, or even maybe more recent than that. Okay, so then this gets to probably the most interesting part of the talk, which is that I started to see rocks in places that I think are a surprise. So the first is known in the literature. These are in distal rays and at crater antipodes. So Josh Banfield wrote this beautiful paper about Tycho antipode having impact melt deposits and rocks, shown here on the bottom. And I wouldn't have bet that these would be there, but clearly they are. So the very youngest, biggest impacts can trigger motions that allow rocks to come to the surface, or they can have melt that then breaks up into clasts over 100 million years. One of the things that's interesting about these is they're not high curvature areas. They just sort of follow the rays. They follow secondaries. And one of the questions I ask is, like, what fraction of these materials are local versus actually the blocks have ejected themselves? I think that my view is they're mostly local, if you look at something like the Oberbeck and Quaid work in the 70s. But I don't think it's obvious in any given instance that you can prove that. I think it's an interesting question. And so I'd like to sort that out. The other area, class where rocks are a surprise to me are places where, like, they're just rocks in the highlands of the moon that have no obvious source. And so this is the category that I really wanted to bring up here, because I've been breaking my eyeballs getting these glasses now, right? Staring at LROC pixels in the south polar region of the moon for Artemis 3. And there are just these mounds of areas that don't have an obvious source crater. They're not clearly at the antipode of anything, and they just have rocks on them. There's rocky areas that are just rocky. I don't get it. I think they're young. Like, I think that, these arguments that there's this demolition job going on, I think is real. But like I say on the slide, if you'd asked me in 2023, before I started looking in really detail at some of these LROC images, whether these were likely to be there, I would have bet no. I would have said, they're usually around fresh craters, usually on steep slopes. Those are the places that we see rocks. And then there's a few examples here. This is an example in Slater Plains. This is not a high slope area. It's just sort of a mound in the middle of nowhere. In the region of the Artemis landing site. But don't take that for anything, because it's not a particularly interesting place. Here's another example on the central peak of Mercurius crater. This is supposedly an Imbrian age crater. If you look at the mapping, it's only 64 kilometers. The central peak's just covered. It's a flat surface, and it's covered in rocks. Maybe you can explain this with curvature. Maybe it was rejuvenated by some sort of process, but I don't get it. So I'm open to suggestions. And so in summary, I think that there's more to understand about the provenance of rocks on the moon than perhaps I had anticipated in 2022. I think that, the remote sensing is starting to really point to the idea that not every rock has a clear provenance. We really want to go after rocks that do have a clear provenance, right? We want to get ones where we can link them to geology. But I think there's still work to do here to understand the lunar rock cycle. So I'll just stop there. Thanks.